Okay, so welcome everyone to the next AMR-RMA talk. This is the Association for Mathematical Research Recent Mathematical Advances. Our speaker today is Eva Miranda of the Universitat Politècnica de Catalunya. She received her PhD from the University of Barcelona and taught there and Toulouse and a few other places before returning to UPC. She's the recipient of many awards and honors, and if I took the time to tell all of them, we would be here all day and we would never get to hear her lecture. But among them are the De Roots Prize from the Royal Academy of Belgium, the Bessel Research Award from the von Humboldt Foundation, the Chaire d'Excellence of the Foundation Sciences Mathématiques de Paris, and she was an invited speaker at the 8th European Congress of Mathematics and the Hardy Lecturer of the London Mathematical Society, the Nachdiplom Lecturer of the ETH Zurich, the Gauss Chair at Göttingen, many other awards and recognitions. And we're delighted to hear today about the shape of Undecidable. Please take it away.
Thank you. Thanks for the presentation. Thanks for inviting me here. It's a great honor. And I have to say that what I'm going to explain is joint work with a number of people, mainly with Daniel Peralta Salas, who has been a collaborator probably of everything I'm going to explain today. Also, my former student Robert Cardona and Ángel González Prieto and Isaac Ramos have been main characters of many of the results that I'm going to explain. But what I want to focus today is indeed to finish with a question more than a sentence like, what is the shape of the undecidable? So we are starting to understand what's the shape of the undecidable, but this is still a little bit towards the end of my talk. I'll present some work in progress with Urs Frauenfelder, Ángel González Prieto, and Daniel Peralta Salas, which wants to understand what is this shape. So the motivation for the title comes from a question we asked ourselves a long time ago with Daniel Peralta Salas to understand if there was we want to discuss today dynamical systems that behave like computers. So the trajectory is moving along a trajectory is equivalent to computing with a computer. You choose your computer, Turing machine, or whatever, doesn't matter. And what we wanted to understand if there is some natural signature of the dynamical system that allows you to understand whether a certain system is Turing complete or not, as the definition of Turing completeness is quite involved. And this takes us to to Smale, who had this idea that the shape of chaos, or anything connected to chaos, should have the horseshoe. And indeed, horseshoe is going to be also important and associated shift in our presentation of what is a Turing-complete dynamical system. So I'll try to present things little by little. Feel free to interrupt if you have questions. First, the shift, we all know, the shift is just a transformation on the set of by sequences. The Bernoulli shift just moves to n plus 1, the set of sequences. And what I'm going to talk today concerns the Bernoulli shift, but more a generalization that it's quite difficult to make a picture of it, because the Bernoulli shift, after all, we can make a picture like in this Smale horseshoe. And this is one of the observations of Smale and many people working with this problem in the theory of chaos, of the classical chaos. And now we want to sophisticate a little bit more this definition of Bernoulli shift. And for that, we get our inspiration from Chris Moore from Santa Fe Institute, who did his PhD in investigating, indeed, a new form of chaos. Indeed, it was in Science advertised as mathematician discovers a more complex form of chaos. And here we see a kind of puzzle of a square in which there is a kind of change of order of the pieces. And indeed, with this picture, in which we need to think that this, indeed, it's a square Cantor set, Moore generalized the notion of shift to what he called generalized shift. And indeed, this generalized shift is very important because he proved that there is a correspondence between generalized shifts and Turing machines. And this is going to be very important for us. When this correspondence occurs with a special type of Turing machine, which is called universal Turing machine, then we get the phenomenon of Turing completeness. So today we want to investigate this. And for that, the definition of generalized shift is a bit more complicated. In a way, now we have the shift, the standard shift can be seen as a particular case of generalized shift. For the generalized shift, we are going to act off by sequence, and we're going to be able to modify two parts of this by sequence, certain positions, R and L, with two different functions. The function f takes values in z and wants to be the generalization of the shift. The function g, what it does is to assign in a window of length L in this by sequence long tape, we could think, just we take a window of length L, we change that window. Okay, so how does the generalized shift how can we compute it? Indeed, it's quite messy, the definition. First, we compute this f on the sequence, g on the sequence, okay? And then what we do first is to modify this sequence on this space, on this strip, which we call dg, using g, okay? This is gonna change, this is gonna cut a finite window inside this long by sequence, which we can think as a long tape, okay? And we cut it out and we modify it. And then we shift with using f of s. So the shift is not constant anymore. The shift depends on the sequence. So we compute f and g, we modify first by g, and then we shift by f. So this is more complicated than the standard shift. And indeed, why it's so complicated? Because indeed, with this, we can indeed perform computations like in a Turing machine. And this is one of the things that Moore proved. So as such, the definition is not very compelling. Can we make a picture of this definition? Looks hard. The end of my talk goes towards understanding if we can do the picture of this definition, and if we can understand by looking at the dynamical system and the phase space whether there is a generalized shift to which we can associate this in such a way that the movement of the trajectory of the dynamical system is equivalent to computing with this generalized shift. The standard shift appears as a particular case in which we consider G as the identity, okay, and F constant equal to 1. This is just a particular case, so the standard shift is a very particular case of the generalized shift. And Moore proved, and this is very important, that there is a correspondence between generalized shift, Turing machines, and mappings of the square Cantor set with certain properties. And okay, this is quite theoretical, so I'm going to go to some practical ideas and then I'll go back to the theory. So this is Saint-Malo in March 23. We can see that there were big waves over Saint-Malo. This is not a surprise, but in 23, they were particularly high, okay? And last year, we had this asteroid which was about to fall on us. Every day there is news. Today there was also a news about an asteroid falling on a volcano. I don't know. I didn't have time to follow it and put it on my slides. But there are things that, in a way, we cannot predict. So now a practical question. What would happen if we throw 29,000 rubber ducks to the ocean in Saint-Malo? Why would you do that? Wait, you'll see. Please don't do it. It's not a good idea. Okay, we are trying to preserve our seas and oceans, so not a good idea to throw all these rubber ducks. What would happen if we throw these rubber ducks on space? Why would I be asking such a question? Indeed, this is based on a true story. In January 1992, there was a carrier that had a cargo containing, among other, 29,000 rubber ducks, and because of a storm, lost all the cargo. And then these rubber ducks, which were rubber ducks like this is the standard one. As I said, was in Tromsø, so I had to buy the typical one from Tromsø, so this beautiful Viking. Um, then these rubber ducks had been doing a lot of excursions, and indeed, the movement of the rubber ducks was used to improve the numerical simulators that were following the flotsam that has been lost. So what's surprising is that these rubber ducks appeared in places where they were not expected. For instance, 10 rubber ducks appeared in Sitka in November, and these rubber ducks were lost in January. In July 2007, it was advertised everywhere that thousands of rubber ducks would appear in the UK. Apparently, just one rubber duck showed up in Scotland. Indeed, the rubber duck story is so popular that there is even a book, Moby Duck, that concerns how these trajectories of the rubber ducks have been used to improve the oceanography, etc. So they are sort of important. And today, why I'm talking about rubber ducks, because I'm talking about this factor of lack to predict where these rubber ducks would appear. Of course, we are thinking that the rubber ducks are moving 3D, because if they are moving 2D, this is an integral problem. So we are understanding that these rubber ducks are moving 3D on this fluid. And then what I want to connect the rubber ducks is to the halting problem. The halting problem is the problem of understanding whether there exists a general recipe, an algorithm that tells us whether an arbitrary given process with a specific input data will eventually stop, which means will reach the halting state, or will continue to run forever. In 1936, Alan Turing proved that the halting problem is undecidable, and by his own proof, he gave the definition of the first model of computer, the Turing machine. So indeed, we could be thinking that this is the beginning of computation. Now, what does Turing have to do with the rubber ducks? Remember the simulator that I was mentioning, which is called Oscures, could not localize all the lost rubber ducks. Indeed, the oceanographers who were working with these rubber ducks in Graham and another one, they made an experiment which they were throwing bottles of water with messages inside the bottle, and they realized that only 2% of the messages in the bottles are recovered. And you say, oh, maybe people just got this bottle and they didn't dare to ask, look, I got the bottle. But it seems that the message is not, I love you. The message is, this is worth 50 pounds. So these people should have reacted to that message. So many bottles then are also lost with these messages. So the question we want to answer today, and indeed in a metaphorical way, what if finding the rubber ducks is also an undecidable problem? And if you replace the rubber ducks by trajectories of a fluid, this is one of the questions we are going to answer today. Can we associate a Turing machine or supercomputer to the trajectories of the rubber ducks? In doing so, we will try to understand a little bit better this idea of what is the shape of the undecidable. Though by doing so, initially we will not understand it. We will need to work a bit harder. So first, what we will do is to associate a Turing machine to these to the trajectories in a fluid, which can have viscosity or without viscosity. So we will deal with the Euler equations, also with the Navier-Stokes equations that are so popular. And we will also deal with very simple systems like billiards. Billiards, even if very simple, are able to perform computations. And from that, we will try to extract some consequences. So talking about fluids, who was the first who asked the question whether fluids could compute? Well, this was Chris Moore, the first one, okay? And here in the image, we also have an image of Penrose, because Penrose was asking about the limits of computation and physical systems, so it's clearly related. And also Terence Tao was asking this question in 2019. And the reason for asking this question was to see if we could use one of these fluids that can compute as initial conditions of the Navier-Stokes equations in such a way that this leads to the phenomenon of blow-up. So there is this regularity conjecture on the list of problems in the Clay list that asserts that we know that the equations, the Euler equations and Navier-Stokes have solutions short term. Now the question is, do they have solutions long term? And now everybody starts to think that probably not. So people are looking for a counterexample in many different manners using machine learning, etc. And turns out was trying to find initial conditions that were complicated enough that could lead to this blow up. And there is a reason why he was looking in this direction, because he had been working with the average Navier-Stokes equation, and this is the way he got indeed a blow up for this particular type of PDEs. Okay, now from fluids to heavens, I want to also connect these questions to the problem, to the n-body problem and problems in celestial mechanics. This would then link to this problem of the satellite. And the n-body problem is a classical problem known not to be integrable when n is equal or bigger or equal than 3. We have three bodies. They are attracted to each other by gravitational force. Okay, and it's not known how to integrate this problem. What this problem has been studied and chaos has been completely been understood in the restricted versions of the three-body problem, in more general versions very lately by the work of Marcel Guardia and Jacques Fejos. So we want to understand if not only classical chaos, but also this kind of new chaos of the fact that chaos comes from the undecidability property of the halting problem by Alan Turing. And this was indeed, we can find this conjecture in several places. Probably the first one is in the book by Stephen Wolfram, A New Kind of Science, where he poses this question. Okay, so we want to consider this kind of problems. We want to consider whether fluids can be complicated, so we can use the movement of a trajectory in a fluid to compute. Also, can we use the movement of a trajectory under an n-body problem to compute? These are the questions we are gonna try to address. And by doing so, we will be understanding a little bit better this definition of generalized shift, which is quite abstract as such. So this, I want to make a point. What I'm going to explain today is about not classical chaos, is about this kind of chaos that I call logical chaos, okay? The classical chaos was studied by Lawrence and by many people, and the definition and the problem of classical chaos is a problem on sensitivity on initial conditions. The problem of logical chaos is a problem of totally impossibility to know whether, for instance, a particle will enter into a certain open set or not. Okay, so the classical definition of chaos, coined by Lawrence, is, as you have here, when the present determines the future, but the approximate present does not approximately determine the future. So if you change slightly the initial conditions, you are lost. And when I was visiting Observatoire de Paris, as Alex mentioned, I have been there many times, also at Chair d'Excellence, but I was always very interested in what they do and how they work. And Jacques Lascar is there, and he was in 2009, he was doing an experiment that I found very interesting. He did over 2,500 simulations of the solar system, and just the difference of 1 millimeter to the distance to Mercury could lead to fatal results, right? In particular, could lead to collision in the solar system. And I remember attending his talk and getting very scared by looking at his presentation. So this this that Jacques Lascar was mentioning is classical chaos. That he proved, if you want, numerically, and has been proved very precisely recently by many people, some of them at Observatoire. And well, the butterfly effect, that is the classical name, as we understand chaos, has been very popular. Now there are many films going on, and indeed, this is the title that Lawrence gave of a talk. It looks like the title of a film, but it's the title of a talk, and it's what people remember. That's the flap of a butterfly's wing in Brazil, set off a tornado in Texas. That's what we hear from the butterfly effect. But okay, let's talk about Turing machine and what I mean. Of course, I'm not an expert in computer science. I'm accidentally here, and I think like with all my collaborators, we ended up here. And it's very interesting because, of course, the language of people working in computer science is different from our language. So it took us a bit to understand. So for a talk, I just want you to think, for the talk of today, that a Turing machine is a printer. So we're going to think that we have a printer, and this printer that we have here is a printer of states on a long tape. And this tape has an alphabet that we can always assume is an alphabet formed by zeros and ones, and this is what we're going to assume today. So we print states over some symbols using this printer, okay? And among these states, there are two states that are very important. That is the initial state and the halting state. Okay. Well, depending on the books and indeed depending on the papers that they even write, this halting state is just one state or several states that lead to halting. Here I simplified myself. I just choose one halting state. It's everything. It's equivalent from a mathematical perspective. So I want you to think of a Turing machine as a printer, and then indeed the user's guide of the printer is indeed the mathematics. It's indeed what we call the transition function. Okay, so how does this printer work? If the current state is just the halting state, then you hold the algorithm, and then the output of the computation is just the tape. Otherwise, right, what we do is to apply this rule here that you have here, delta Q T0 goes to Q prime T0 prime epsilon, okay? And you replace Q with Q prime, T0 with T0 prime, and T with the epsilon shifted tape, and you shift with 1 or 0, you don't move, or -1, and the way you think of it is that when you have a +1, the tape is going to shift to the left, so the printer is going to shift to the right. So this +1 is to the right, the printer to the left, the tape. And here we have an animation of this transformation up there in which you change 0 by 1. Okay, this is what it does. You change 0 by 1, and then you move, the printer moves to the right. So the tape moves to the left, and this is this +1 that you have here. Okay. Okay. So I want to make a point how to relate this square Cantor set and the Turing machines. Okay. And it's the idea, it's very simple. And this, once you understand this, you completely understand what's the idea that Moore had in his head. If you take the tape just as these collections of zeros and ones and the state here, then you have a collection of zeros and ones, okay? And you may consider, for instance, the one on the left as coefficients of the ternary expand, and this gives you here the x that you have on the right. And you can do the same for the ones on the left, on the right. Okay, you take the zeros and one on the right. Okay, and then you take these as coefficients of a ternary expand. Okay, so in conclusion, if I am computing with a Turing machine and I look and I take a picture with my phone, now I look at my phone. Okay, And I see that I'm scared because I have a message of one of the persons who is there listening, and I was scared that maybe nobody was listening to me because this is the fear of an online talk. Now I see it's okay. So I take my mobile phone and I take a picture of the Turing machine computing. Okay, and in that precise picture, I have this precise collection of zeros and ones. Okay, this gives me these coefficients. The ones on the left, they give me the coefficients of the x on this square counter set. And the one on the right, the coefficients on the y. Okay, because I just take the ternary span. And therefore, this point here that it's in red, it's going to be a point on the square counter set. When this Turing machine continues to compute, this red point is going to be jumping from the square counter set to another point on the square counter set. And I think of this as a mapping. Okay, so this is why Chris Moore was thinking that computing with a Turing machine is the same as a mapping from the square counter set to itself. Okay, that's the very deep and important idea we're going to be working. And indeed, he completely characterized and realized that this mapping correspond to this generalized shift. So he also had a way to associate to this f and g of the generalized shift a mapping on the square counter set. Okay, and this mapping on the square counter set can be done by blocks. Okay, and in each block can be seen to be linear and can be seen to preserve the area, etc. It's very difficult to understand is, do you have a characterization of the transformation such that this is universal? This is more complicated question. Now it comes what is going to be more important for us, which is the definition of what is a good association. So you have your dynamical system and you have your particle that can be this rubber duck or a particle on your dynamical system, and you do an association, okay, of the Turing machine, of the computations of the Turing machine, that it's a discrete set, okay, on this continuous set. You can do it in many different ways. There's not a unique way to do it. But what's very important, in order for this association to be good, we need this association to be Turing complete. It means if I have a vector field, I say that it's Turing complete if it can simulate any Turing machine. How can you detect this in practice? A way to detect this in practice has to do with the definition of universal Turing machine, that it's very worthy, but it leaves as a trace the following. This is equivalent to the halting of any Turing machine with a certain input that has to be computable is equivalent to certain trajectory of this vector field enters an open set. And this open set has to be computable. Which means, what does it mean computable? It means that the coordinates have to be given by a Turing machine. Okay. So for instance, if you think in terms of the example I was putting of the rubber ducks not arriving in the UK, you may think of this neighborhood, this in green, as a neighborhood of the UK, and the particle, the rubber duck. So it's undecidable to know whether the rubber duck would enter if the association that I do to the movement of water and the Turing machine has this property of Turing completeness. This is exactly what we are going to prove. However, what I'm not going to be able to prove is this particular rubber duck follows the association that we will do. What I will do is to find a solution to the Euler equation that is Turing complete. Okay, I said Euler equations, and here we have the Euler equations. These are the classical Euler equations that we explain to our students. This is a PDE that depends on time. Okay, x is the velocity of the fluid flow. Okay, p is the pressure, and then, well, the second equation, that it's divergence free, it means in a way geometrically that the flow of the vector field is volume preserving. That's our idea, and this is on R3. And then this is the first equation, is the classical Euler equation, where we don't see a Riemannian metric, but there is a Riemannian metric, the Euclidean metric. What's interesting, and this is an important contribution for many people, including Alberto Enciso and Daniel Peralta Salas, is that we may look at this kind of problems from a Riemannian perspective. So in associating a Riemannian metric, okay, then we may look at this equation up there as some equation associated to the Levi-Civita connection associated to the metric G. And this allows to express the equations in a more compact and geometric way. Now we are geometers, and now we want to deal with the solutions of these equations. And as we are geometers, not analysts, we take the easiest possible case in which x does not depend on time. So this would correspond to stationary solutions of the Euler equation. Okay. By the way, the Euler equation, I didn't say it, I was too quick, but remember the Euler equation, the fluid doesn't have viscosity. Okay. So if you have viscosity, this does no longer apply. You need to use the Navier-Stokes equations. Okay. The equations can be written this way. And what's very interesting is that by using the metric G, we are able to dualize the vector field X. Okay, we just contract this vector field with the metric, and this gives me a one-form alpha. And this one-form alpha satisfies these two equations, which we can now read as a certain two-form, which is the differential of alpha, contracted with X, again, a one-form, being exact. Okay, and the function that makes it exact is the Bernoulli function. The second equation, that it's a divergence-free vector field, can be realized a certain form being closed. Among the stationary solutions, a special important class is that of Beltrami fields. Beltrami fields are characterized by being proportional to their curl and divergence-free. Okay, and among the Beltrami fields, we find very famous vector fields, like the Hopf fields in the Hopf vibration or the ABC flows. Both are examples of vector fields on compact manifolds, three-dimensional. By the way, today I'm going to be talking about the three-dimensional case. All these can be extended higher dimensions. What about the Navier-Stokes? Well, in the Navier-Stokes, we have an additional term that corresponds to viscosity. Okay, so we expect that the problem will be much harder because of this viscosity term. So in particular, will we have such a beautiful way to deal with the equations? By the way, don't forget that here we have a one-form alpha associated to the Euler equations, and this one-form alpha will have a geometrical meaning in some slides. It will be a contact form. Now, when we add the viscosity, then this becomes, a $1 million problem. And still, this is unknown if we are going to have these singularities, though everything seems to be pointing to yes. In the last months have been interesting, as now with artificial intelligence, we are able to say many things and to test many different things. But this seems that up to date, this has not been proved yet. The existence of blow-up. So the idea of Terence Tao was to use some initial conditions which behaved like a Turing machine. And so the first question he asked is there is a solution to the Euler equation which is Turing complete. He asked this question specifically. And this is a question we can answer in the positive. So we were able to construct a solution to the Euler equations, which is Turing complete. Okay, and what we do is indeed to associate a solution to the equations just by using stationary solutions, this kind of Beltrami fields. Why? Because, well, in our hearts, we are geometers, and indeed, we have been working, in my case, with symplectic geometry, and contact geometry is next door. So, indeed, our initial idea was very simple. We thought of the transformation of Chris Moore, which is a transformation of a disk on a disk, which is area preserving. And this transformation, initially, Moore was thinking of the square Cantor set, but we can extend it to a smooth diffeomorphism of the disk, which is identity close to the boundary, okay? And then we were thinking, okay, maybe what we need to find is a Beltrami field, okay, in dimension 3. So first thing, now we have something in dimension 2. Maybe we can find a vector field such that its Poincare section, it's precisely the mapping of Chris Moore. And that's exactly what we did, okay? In order to do this, we used a very interesting connection between contact geometry and Beltrami fields. Okay, indeed, first what we did is to look for a particular type of vector field that has to have this property that the time one map has to be area preserving. So in particular, we were looking for vector fields that preserve the volume. And among the type of vector fields that preserve this volume, we were looking for what we call red vector fields. Now, red vector fields, okay, are associated to contact structures that exist in dimension 3. And just my 1 minute lesson of what a contact structure in dimension 3 is, this is given by the kernel of a one-form alpha that satisfies that the opposite of integrality. So alpha wedge d alpha is a volume form. In particular, this doesn't vanish, that this means in practice that the kernel of alpha is not integral. If you try to apply Frobenius, you realize that it's not integral. So when you have, if you have a Beltrami field, then it was Ender and Grice who proved that there is a correspondence between Beltrami fields and red vector fields. So if you can solve your problems with red vector fields, then a reparametrization of your vector field will be a Beltrami field. Okay, so we were using this result by Ender and Grice. Okay, and that's exactly the correspondence. So Beltrami fields, okay, can be seen up to reparametrization as red vector fields. And in doing so, we proved, and because the proof was very simple, we just did this kind of disk. And then if you have any contact manifold, then you just do a surgery to insert your, this is what you have. What you have is an annulus, okay? So you just insert your annulus inside whatever contact manifold you have. You do a surgery and it works perfectly. So we proved, indeed, all the computation happens inside this annulus, and outside we don't care. So the theorem we proved is that we did this with Robert Cardona, with Daniel Peralta Salas, and Fran Presas. There exist solutions to the Euler equations which can simulate any Turing machine. And indeed, these solutions are Beltrami fields. Okay? So because the halting problem is undecidable, right? If this can simulate any Turing machine, in particular a universal Turing machine, then the corollary, which was pretty surprising, is that there exist undecidable fluid paths. So there is no algorithm that that decides whether a trajectory will enter an open set or not. So we had done this, and I remember talking to Daniel and say, "Oh, let's try to do something with Navier-Stokes." Daniel, impossible, impossible. But it turns out that there is also some geometry behind Navier-Stokes equations, and it's indeed very simple. The idea is very simple. If you take an harmonic vector field, then this harmonic vector field will be a stationary solution of the Navier-Stokes equations. And also, in the same way, Ender and Grice constructed a correspondence between red vector fields and Beltrami fields, here there is a correspondence between these harmonic vector fields and red vector fields, but of a cosymplectic structure. So you do have a geometrical structure which is cosymplectic. This is given, if you want, by a pair of forms, alpha and beta, and the form alpha now satisfies the integrability condition. Alpha wedge d alpha is 0, and the form beta is just a symplectic form on the leaf. So a cosymplectic structure is a codimension 1 symplectic foliation of a very particular type. There exists a vector field which is transverse to all the leaves, which is this red vector field, that it's important. So not every codimension 1 foliation, symplectic foliation, will be of this sort. So in doing so, we played exactly the same game, but on a different battlefield, that is of Navier-Stokes. And something very interesting is that this stationary solution is a solution for any value of the viscosity. It's also a stationary solution of the Beltrami fields. So we have a kind of construction that is uniform depending on this viscosity. And that's something we did with Soren Deer, one of my PhD students, Ángel González Prieto and Daniel Peralta Salas, very recently, just in time to give this talk. Okay, and something we did in December with Isaac Ramos is, well, you may think, well, you prove that you can always associate a Turing machine to a fluid, because fluids are very complicated, blah, blah, blah. You can do a billiard, and you can do a billiard with one ball. You say, oh, there's no point in playing billiard with one ball. This has to be the 8 ball. Yes, it's true. But what's interesting is that then we could prove that if you give me at any Turing machine, okay, I can make this, I can construct a table, and the form of the table, the shape of the table is much given by the Turing machine in such a way that playing with this ball is equivalent to computing with the initial Turing machine. And this is a result we did with Isaac Ramos, who is a master student. And it's very easy. Like, it's what I shouldn't say it's very easy. It has a very interesting point, but it's very easy to follow this construction. So in a way, the construction of billiards has something interesting, as many systems, like I said, the collision that I was so scared of in the solar system, and collisions are also have this model that close to collision they behave like a billiard. Also, does the uncenter problem behave like a billiard? So the fact that this very simple two-dimensional billiard, just with one ball, is Turing complete, gives us the idea that maybe many problems in celestial mechanics can be Turing complete. For instance, you can deform in a way and get some smooth Hamiltonian realization. So this puts us exactly in the right place, right? What about the asteroid? What is the status of, can you give me examples of problems in celestial mechanics that are Turing complete? Okay, if I have to choose a picture, an idea, then this is like putting my rubber duck, okay, on this asteroid, and then it's undecidable where this asteroid will go. Okay, this would be the video corresponding to this idea. And this idea is quite interesting, not only from this abstract perspective, but from a practical perspective. Nowadays, we have so many satellites out there that maybe this space traffic is reaching what I call the Turing scale. So the conjecture that initially Stephen Wolfram formulated, we are working on it, and it's very hard. And Stephen Wolfram came to talk to us, and we spent 6.5 hours talking about this and many other interesting problems. But still, we don't know the answer. But what we think, our conjecture is a bit simpler. It would be great to prove that the three-body problem is undecidable, but maybe what we can prove is that there exists an n such that the n-body problem is Turing complete. And then from that, maybe we can go and improve this n until we get n equal to 3, right? So let me share with you, because I have been speaking for a long time, but I still need to get to the most exciting part of my talk. What is the hint that makes us believe that we can prove that some variant of the three-body problem is Turing complete? And this takes me to the classics. Moser proved indeed that the Bernoulli shift, the first example that I gave of shift, Bernoulli shift, can be embedded in the Syndikov problem. And he did it in this, well, it's not a paper, indeed, as you see, it's a book. And it's a fascinating book that I have read and I will read, and it has many, very interesting things. In particular, he proved that a Bernoulli shift can be embedded in the Syndikov problem. The Syndikov problem is a particular case of the restricted three-body problem in which we have three bodies, two bodies, same size, okay, moving on ellipses, very important, okay, and then we have a third body which is oscillating between the two. And here I'm borrowing a very nice presentation of this problem by Robert Grist. Here we have the two bodies. They move in two ellipses, okay? And you see the third body oscillating. We could be here. You see it oscillates. In particular, this third body crosses along z equal to 0, if you want. And indeed, Moser had a fascinating idea, which is, okay, he counted how many times this, what he called the primaries, let me put this again. The primaries go around themselves when the third body crosses Z. So when the third body crosses Z, we count how many times they spin. And with this idea, he created a sequence of points which looks very much like a Turing machine, a long tape. But it's a long tape in which there is no computation because he just has a long tape with a sequence of numbers written there, okay? But he was able to put the shift. And how he did it, this belongs to the classes, this is in this book, okay, what I'm explaining here. He did more or less, he associated from this sequence of times that it goes around, okay, counting how many excursions, in each time they cross, how many times they spin around. This is exactly what this number means. And then he represented this on a square counter set, indeed. And then he realized that this is conjugated to the Baker map. Okay, so again, here we have, so he was able therefore to put the shift inside. Okay, so he embedded the shift inside the Sinikov problem. And this has been super important in particular for this last study I was mentioned of Guardia and Jacques Fejos concerning chaos, because they had a very, very fine control of these excursions, and this was used by them. And again, we have here the shape of chaos. So now let's go to what we are doing now. It means that this is still not an archive. Maybe this is still not completely proved, but I'm gonna say it. This is the joint work with Urs Frauenfelder and Daniel Peralta and Ángel González Prieto. And so we believe the Sinikov problem has the shift. Therefore, if you look at the generalized shift, in a way you have the F, but you miss the G. Okay, so I would put this still as a conjecture. You see, this is exactly very, very clever. I didn't put theorem because I don't know. I would like that it's a theorem, but we still don't have the proof. But we know how to prove it, but it's not written. That the Sinikov problem can be upgraded to a Turing-complete system, so generalized shift, by adding some particular boost. So boost would be changing the velocity of the particle when it crosses z equal to 0. And we believe that this would generate this would generate something equivalent to generalized shift in the Turing-complete generalized shift. And indeed, while discussing the Sinikov problem, we started to realize that indeed the Sinikov problem is extremely close to the simple pendulum. Indeed, while the Sinikov problem, if you take that the eccentricity of the ellipses, if it's circular, then it's an integrable problem, okay, like the pendulum. But then when you perturb the simple pendulum, you get qualitative, something very close to the Sinikov problem, but once the Sinikov problem is indeed projectivized in a way that when you have, for instance, the pendulum that goes here and around, you are allowed to look at this as a projectivization. And so, in particular, this would allow us to prove things about also the perturbed simple pendulum as Turing complete. Okay, but we still don't know how to embed all this in an n-body problem, if you want, because Okay, the Sydnikov itself, it's a particular case of the three-body problem, but when you add the boosts, then I don't know how to embed this by adding, you think is this boost equivalent to a comet going very close and just flipping around, but then you need to have this comet for the computation. So unclear if this is really an n-body problem. So we are trying hard on these ideas. And this, now that we have been playing quite along with this idea of Turing completeness, what is the shape of the undecidable? I've said that in most of the examples we do have the shift. And therefore, once you have the shift, you automatically have this positive topological entropy. I remember that one of the first questions that we got, indeed by Leonid, when we started to work with this, is what is the topological entropy of the construction we had done? This first construction I explained, the one of the proceedings of the National Academy of Sciences. And indeed, the entropy is positive because you have a shift, you have a horseshoe, and you have everything you want. But indeed, we also have examples, very natural, of Turing-complete systems with zero topological entropy. Indeed, this is in a paper we did with Robert Cardona and Daniel Peralta Salas, in which, indeed, we were, in the construction we did before, we were changing the Riemannian structure, and this is our secret, right? But we were able also to provide Turing-complete systems if you don't change the Riemannian structure. And this is the Euclidean case. But then what happens is that you get a system with high energy. So not very practical to build that computer. And we did a construction, which was indeed a construction where all the computation was taking place on a two-dimensional submanifold, but this was in dimension 3. And in a way, somehow artificially, we were building a kind of, how to say this, a kind of cylinder construction over this computation. The computation was taking place on a two-dimensional manifold. So in particular, the invariant set, which was a sphere, okay, was preserved. So in particular, of course, the topological entropy of this was a surface is 0. But it's Turing complete because this surface, which was a sphere, is a sphere in that paper, is in the invariant set. So we do have examples with zero topological entropy, which at the beginning was very surprising, but now it's no longer surprising. We completely understand what's going on. First, we devoted, a paper and a lot of time with Robert Cardona and also a former student of us that started to collaborate with us, Renzo Bruera, and then went quickly to do a PhD in PDEs. He ran away. And Daniel Peralta Salas, we had posted the paper on arXiv, and then Ville Salo, who is an expert in these topics, sent us an email the day we posted on the arXiv. This was very surprising, knowing he knew how to answer the open questions at the end of the paper. So this is how he became a co-author. So this is why the paper has 5 authors. Because Ville Salo was able to construct not only, let's say, an actual Turing machine with 0 speed. So not only that the system that was embedding the Turing machine had zero topological entropy, but the Turing machine itself had 0 speed, therefore 0 topological entropy. And this at the beginning was super surprising. And there, for instance, in that paper, we give conditions to have positive topological entropy, and we call these branching Turing machines. And these are Turing machines that admit essentially, to say it very quickly, an invariant set. And on this invariant set, it acts like a shift, the Turing machine itself. Therefore, once you have a shift, again, of course, you restrict to the subset. There you get this positive topological entropy, and therefore you get some construction with positive topological entropy. But now we completely understand what's going on. So topological entropy is not good enough for us. Topological entropy is not a complete detector. Indeed, this idea of branching symbolic models, which are symbolic models that look at invariant sets, create in a natural way entropy because you can restrict to the invariant subsets, which is something beautiful of this Turing complete system. And indeed, maybe entropy is too vague. Entropy is a big word, but you always need to adapt it. So you need to take a finer clock. Entropy is not good enough. You need, for instance, in this construction that we have with Villesalo in this paper, the time it takes for the machine to compute is very, very long. So if you take a sequence of time, then you can see positive topological entropy. So the statement is that you have naturally, if you have a Turing complete system, you have some natural positive topological entropy, which is maybe not topological entropy itself, but a refinement, like sequence entropy, which means you restrict to some times, or a slow entropy. And that's exactly maybe the conjecture that I should have written here. Conjecture, there is a refinement of entropy, there is a good notion of entropy that sees and measures and can measure not the complexity of the system, but the complexity of the computation. And this is sequential entropy or slow entropy. We are now testing which one is better. And indeed, this took us to an interesting thing because we were trying to prove things that seemed very obvious. Okay, for instance, well, an integrable system should be, it's impossible that it's Turing complete. Come on, let's try to prove it. And there was I said, yes, I can do it. Okay. And I spent a long time making wrong proofs. It was a bit disappointing because it's very easy to take as a starting point. I take some action angle coordinates, but of course you need to have everything computable, right? Therefore, you cannot start writing a proof as you were doing a proof in symplectic geometry. You have to be very careful. So what we have been able to prove is that regular integrable systems with compact leaves cannot be Turing complete. And the reason, and this is also a fine invariant, is distality. So every system that is given by translation of groups, in particular integrable systems, and also degenerate under some constraints, non-degenerate singular integrable system under some constraint, not always. For them, you can check that they are distal. Okay, so indeed, to have Turing completeness, you need to have non-distality. And the notion of non-distality is better than the notion of entropy because you need to look at the infimum, but just after a certain iteration of time. And this is enough. So entropy gives you too much information that sometimes can be misleading. So the conclusion is that every Turing complete system has to have proximal pairs, so it has to be non-distal, so this infimum has to be 0. This gives us a consequence that regular integrable systems with compact leaves cannot be Turing complete. However, if you have, for instance, even a system with an hyperbolic singularity, you can put the computation on the singular case, on the invariant singular set. So, so yeah, the conclusion, and I think the conjecture is Turing complete system may have 0 entropy, but have positive sequential entropy and positive slow entropy. And again, I still didn't describe fully the shape of the undecidable, but I hope I gave a better idea of this. I'm done.
Thank you so much.
Sorry.
Thank you for the beautiful lecture. Do we have questions? Well, I have a question.
Yes.
So, if you believe that the universe is a universal, I mean, that an n-body problem maybe is a universal Turing machine, then our particular universe, any guess what it might be computing?
Yeah, indeed, this is a very good question. We're getting to the philosophical. My friend Raymond Pierre Humbert says, no matter if you tell me that something cannot compute, the universe can compute, even if you can prove that it's not Turing complete. So I think your question is more philosophical than, but it's an interesting. Probably there is a connection. Indeed, I had a slide for the non-questions because I know that this is a
Uh-huh.
slide. Indeed, I found this by looking at pictures of the I-4, the odds of dying because of an asteroid. There is a question, but Michael,
Uh, yes,
It's,
thank you. Um, I was going to ask, and maybe you touched on this in your papers, whether or not you can apply the methods to classical proofs of undecidability, like that of the piano arithmetic, for example.
that's very good, very nice. Indeed, this is what we indeed the other way around. I have been trying to use indeed to prove the last things that the integrable systems were Turing complete. I was trying to use indeed the other way around. I was trying to check that it had to be decidable. So of course you trying to contradict that it's undecidable, but maybe because I am not very good at that, I have to train myself better. I found easier by giving this geometrical. But your question is very good, and I think we have to explore this. This is a very good question. We didn't start doing this because we are quite obsessed with this three-body problem. Indeed, tomorrow we have a meeting to continue our discussions. But Michael, this is a very good question. Thank you.
Just one follow-up since you mentioned the n-body problem. How do you deal with situations where it's highly restricted because, for example, collinear initial conditions is solvable and therefore decidable? So you have to
Yes,
take out
yes,
these. Yeah. So how do you do this?
yes. So this is not. This is indeed a very good question too, because there is a okay. Very good that you asked this question, because the fact that there are decidable trajectories doesn't contradict our fact. We just need to prove that there is this undecidable, and the set of decidable or undecidable. Indeed, you can indeed construct artificially, not in these natural systems. I could, I could, for instance, take this integrable system situation, and I could put undecidable on a meager set or on a big set. So the fact that there exist decidable paths does not contradict me. It gives me indeed the idea to say, okay, the fact that there are collinear, this gives me an idea, okay, I have to look for non-collinear initial conditions, blah, 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 blah. So it's a very, indeed, it's a good way, strategy, helps me to work. Thank you.
Uh, and actually, to give other people a chance, I'm sorry, I just have one last question, and that is there hope, for example, that your methods can give a proof for undecidability of classic problems like Riemann, for example,
Sorry,
like the
what is
Riemann
the problem?
hypothesis. The
Ah,
Riemann
woof,
hypothesis.
woof, woof.
I know it's big.
It will be very funny. I'm not confident. It's not in my radar, but like I don't want to be one of these 1,000 people who write papers like a false proof of the Riemann. But that, I mean, if you ask me about the P versus NP, maybe
Mm, mm.
indeed, but I have to tell you that we have been there very close to making a lot of errors with my collaborators. I will not name them now. But with one of the collaborators I have named today, we were one day thinking we had something like P versus NP, and then it's very easy to make errors. So we didn't try this Riemann hypothesis. It would be interesting. It's not in my. I mean, we are starting to try to see how we are learning by starting little by little. Maybe in 10 years one
Mm.
of my PhD students will be my former PhD students will be able to deal with that. But that's a good like of course what's interesting is to see if you can give a different proof. This is something that we are trying of something that it's known to be undecidable. This is something we are trying. Uh, and most of the things are undecidable. So it's very funny. And this is something we are trying, but something like the Riemann hypothesis, it's not in our radar so far. Not now,
Okay,
but maybe later. But
no
thank you.
problem.
But thanks for the
Thank
Actually,
you
if
so
you
question.
much,
prove
Very
Miranda.
that
interesting.
If you
Like,
prove that the Riemann hypothesis is undecidable, then you actually prove the Riemann hypothesis because it's a falsifiable. It's something where if there's a zero off the line, there are ways to measure it.
wow.
So
Well,
so that would be a path to a proof of RH is to prove its undecidability.
yeah, but this is what I think that, okay. Like, I think I need to jump through many fences before trying to answer that question.
I think Joel
This is
has
how
a
I
question.
visualize myself with this kind of test that I'm doing myself. Integrable systems, for instance, to check that this was supposed to take me one afternoon, took me longer.
Hey,
And
I had a question. You sort of already answered part of it, but you focused on undecidability, but you could ask similar questions for other complexity classes like exponential or
absolutely,
Pete
absolutely,
space or any of the things that computer scientists study. And so there could be some sort of geometric interpretation of these various.
absolutely.
Yeah.
Indeed, this is a very good question, and this is one of the questions that we have on the table. Indeed, this is really a question we have on the table. And we still don't didn't start because we are like little by little. It's the same group of people. I'm working on these problems, but this is really something we want to look into. We started to discuss, but we need to spend more time. I think that once if we finish to prove that this three-body problem is undecidable, then probably in doing so you start to go through to the discussion of the complexity classes in the middle. Indeed, in the proofs, you end up having to deal with the intermediate classes, not only decidable, undecidable, semi-decidable, and all these kind of things. So we would like to do this. Yeah, this is in our plan. In our plan, this is in
But
our plan.
let me ask one more question. Is it conceivable that this might actually lead to some sort of analog computer associated to some classical algorithmic problem that would be a practical way of computing things?
Yes, indeed. Thanks for this question. Like, indeed, I have like, when we started to work with this, like, of course, when we would like to come here with an actual machine that computes with lots of pipes of water, what happens is that we cannot construct this with pipes of water, which would be very nice, and then I would become, a green, super popular scientist. Oh, you can construct energy. But what's the problem? The problem is that the proof that I have explained today, the proof of the that we did using Chris Moore construction changes the Riemannian structure, so it's not physical. So we cannot construct a machine that reproduces this computation. We cannot construct it to say, okay, look, the this particle moving, unless we are able to really change. But the Riemannian structure changed very much inside this tube because the proof uses Moser's path method and Moser's trick. So it gets the form. And it gets the form in a violent way. So it's like this construction, the particular construction I described, is not going to be physical. However, we have another construction that I didn't talk today because I chose what I wanted to talk about, the shape of the undecidable, which uses the idea of putting pieces, assembling pieces with topological, like in topological quantum field theory. And this is something we did with Ángel González Prieto and Daniel Peralta Salas, and we call it topological clean field theory because we wanted to call it TC, but then C was taken by conformal field theory. I mean, like, and then we call it clean. Clean was a well-known mathematician working in the model in which the computation is given as a recursive function, partial recursive function, and that model we believe we can implement. And this is one of like what we call the hybrid computer. We would like to implement it like, this is the computer. But we're still, I mean, this is in my mind. Will I see it in 10 years? I hope I write it in the project. Let's see if I'm able to do it. So far, we started like, I mean, if we prove that the N-body problem is Turing complete, I will be very happy if we can prove it by the end of this year. Let's see. It's very, if I can do it, it will be little by little. But yeah, this is we have a plan to do indeed even to construct. The problem of Turing completeness is that as such is not stable. So if you have to deform, let's say if we take if in our proof we change the Riemannian structure and we need to change it again, then the system will probably not survive, will not be Turing complete when you perturb it. However, there is in the uniform construction of that we did of the Stokes, Navier-Stokes, this one is more stable, and there is a hope that we could try to use it. There is a hope, but we're still far from doing that.
Thank you.
I need more time.
May I ask a question? So you had this theorem that there are non-decidable fluid trajectories. And so how this non-decidability is sensitive to initial condition? Can you comment on this?
So let's say in that particular problem, it's more complicated. In that particular problem, it's more complicated because you have the horseshoe and everything. But another problem, I can cook it. I can cook the decidable and non-decidable paths. In that particular one, it's much more complicated, the construction inside the tube.
Yeah, but if you slightly perturb initial condition,
Yeah,
could
yeah,
be,
yeah. I
could
understand.
it become decidable suddenly?
Yeah, it could because this one is very mixed, the construction, so it could become decidable. In other constructions, it could happen that the decidable path or the undecidable path has zero measure. In this one, it could become decidable. Yeah, it could.
I guess you could go backwards. You could start with a
But
decidable,
but
perturb a decidable.
it's easier for me to answer this question for another system that I can cook up in an easier manner than this one. For instance, the one that I was saying that I can put the computations inside a lower rank of the integrable system. There I can answer this question more comfortably than now. I will try to be more precise.
Thank you.
Yeah, Alex, you have a question.
Oh, no. I was just making a comment that if you just start with a decidable system and perturb it a little bit to an undecidable one, then of course that undecidable one has a near perturbation that's decidable. It was just a trivial comment.
Yeah, exactly. You can perturb it, but if you have, for instance, if you take a system that it's and you can do this, that you have a lot of decidable. I mean, it's not natural system, but you can construct it. You can construct very strange things. You have, let's say, you have a kind of factory to construct. You have a kind of Lego that allows you to put undecidable pieces, and in a perturbation, maybe you don't find them. Because not here, not in this example, I think it happens that you can change the initial conditions and get decidable. Because this example is very mixed. It's like it's a horseshoe, what you have there. Indeed, in that example, we can compute many things because we understood a posteriori, and this is a question that Leonid asked maybe 3 years ago, and now I can answer the question. He asked, what is the topological entropy? Now I can answer it's positive, and I can answer why it's positive, because that machine is what we call this branching machine, that you have a shift inside. And therefore, because you have this shift, then you're going to have very close to decidable and decidable. But I didn't prove this. It's my intuition. Like I would prefer to prove this before answering correctly this question.
Any further questions or discussion? Okay, if not, let's thank Eva again for the beautiful lecture. Thank you so much.
Thank you.